The purpose of this video is just to define the transpose of a matrix. Let's recall a little bit of terminology that we're going to need. That terminology is that of a symmetric matrix or a skew-symmetric matrix. Remember that a symmetric matrix is one where the aijth entry is equal to the ajith entry. So for example, if I look at entry 2, 2, or 2, 1, it's the same as entry 1, 2. In a skew-symmetric matrix, it's almost the same identity, except that aij is equal to negative aji. So now if I look at entry 2, 1, it's the negative of entry 1, 2. Now we're ready to define what the transpose of a matrix is. The transpose of a matrix is denoted with a superscript capital T, and it's pronounced A transpose. If you have a matrix A, what A transpose is another matrix whose ijth entry is equal to the jith entry of A. So if I have a matrix A, in this case it's a 3 by 3 matrix, this means that the first row of A is going to go into the first column of A transpose. That way, if I want to take a special look at entry 1, 2, that's going to go into spot 2, 1 of A transpose. So each row of A goes into each column of A transpose, and likewise, the rows of A transpose are the columns of the matrix A. Here's a couple of examples with actual numbers in them. If I have the matrix A, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, then A transpose is going to be 1, 4, 7, 2, 5, 8, 3, 6, 9. Because 1, 2, 3 in the first row goes into 1, 2, 3 as the first column of A transpose, and so on and so forth. This is an example where we're dealing with a square matrix. So it's 3 by 3, and then A transpose is also 3 by 3. But there's no reason why you can't find the transpose of a matrix which is not square. For example, let's take the matrix B, which is 3 by 1. In other words, B is a column vector. Well, if B is 3 by 1, then B transpose is going to be 1 by 3. The dimensions flip as well. And so my single column vector of B becomes my single row vector of B transpose. By the way, if you like to use the software MATLAB to check your calculations, you can quickly do a transposition of a matrix or a vector in MATLAB by using the tick mark symbol. So for MATLAB users, let me jot this down. You're going to use the tick mark for your vector, V tick mark. I believe you can also write out transpose. So let's make the following observation. If you have a symmetric matrix, then aij is equal to aji. So what this means is that A is equal to its own transpose. And if you have a skew-symmetric matrix, well, that just means that A is equal to -1 times A transpose. It's often convenient to think about the transpose of a matrix in this way. So let's do one more thing to better understand the definition of the transpose of a matrix and work through an exercise. So we're going to show that if you multiply A times its own transpose, well, for starters, it's a well-defined product, and also that you're going to produce a symmetric matrix no matter what you start with. So here's the exercise we're going to sketch an outline for. Let's show that AA transpose is a well-defined symmetric matrix for any matrix A. Well, the first thing to answer is, why is it well-defined? So let's not assume that A is square. Let's let A be any matrix. If A is any matrix, then it's M by N. And if A is M by N, then A transpose is N by N. So if we think about multiplying these together, what we're multiplying is an M by N times an N by M. And these dimensions match. Because these dimensions match, that means our multiplication is well defined. And what we're going to end up with is M by N, M by M. The product A transpose is M by M. So it is well defined, and we actually end up with a square matrix. The next thing to convince ourselves of is, why is this symmetric? So let's think about this. Let's think about this in a special case and then extrapolate what the general argument should be. Well, if we want to see why something is symmetric, what we really want to check is that Aij is equal to Aji. So if I want to look at a specific example, I could take perhaps the matrices 1, 2, 0, 1, 3, minus 1, and the transpose of this matrix. So if this is my A, then my A transpose is going to have a 1, 0, 3 as its first row, because that was the first column of A, and its second row is going to be 2, 1, minus 1. That's A transpose. Now let me multiply these together. This is a 3 by 2 times a 2 by 3, so I expect a 3 by 3 to come out of this. And the entries of this matrix are going to be, well, let's see, I have a 1 plus a 4, so that's a 5. I have a 0 plus a 2. I have a 3 minus a 2. Continuing on with my matrix multiplication, I'm going to have in the second row of AA transpose a 0 plus a 2, 0 plus 1, and then 0 minus 1. And then I'll have 3 minus 2 is 1, 0 minus 1 is a minus 1, and then lastly 9 plus 1 giving me a 10. So this is my matrix AA transpose. And let me write out a little bit more symbolically what's happening here. So here, let me focus on entry 1, 2. So entry 1, 2 is this 2 right here. And I want to compare it with entry 2, 1, which was this entry, and the dot products that gave me those entries. So here, A12 was obtained by taking row 1 of A, that's a vector, and taking the dot product with column 2 of A transpose. And then A21, to which I want to compare it, was obtained by taking the dot product of row 2 of A dotted with column 1 of A transpose. But there's a relationship between the rows of A and the columns of A transpose. The rows of A are equal to the columns of A transpose, and the columns of A are equal to the rows of A transpose. This means that I can take column 2 of A transpose in this expression and rewrite it as row 2 of A. So this line can be rewritten row 1 of A dotted with row 2 of A. And similarly, I can rewrite the second equation. Column 1 of A transpose is really row 1 of A. So this down here is also row 2 of A dotted with row 1 of A. And dot product is commutative. If you have u dot v, that's the same thing as v dot u. So these two expressions right here, these are the same. So this explains why in my example, or at least in a 2 by 2 example, that I get that A12 is equal to A21. And this is the idea of the general argument. If you want to write this down for any matrix, the general argument can be written by replacing your indices 1 and 2 with I and j. So I'll write that down. Replace 1 and 2 in what's written with the symbolic I and j. And if you do that, you'll have your argument for why Aij is equal to Aji, and that explains why the product AA transpose is symmetric.